Hello and welcome back to Machine Learning. I'm Jivita Christie, and in this video, we are going to talk about decision trees. So let's begin. Here is an example of what a decision tree looks like when visualized. So you have root nodes and you have the child nodes and leaf nodes, and decision tree is just a bunch of rules which are if and then rules. So if something is true, you follow this path. If something is false, you follow this path. And that's how classification happens. Here is an example of a decision tree showing you whether you should keep driving your car or you should stop somewhere. Okay, so this is the decision tree for that. So this is the car, and you will keep driving forward. Then you're going to check, is there a spotlight ahead? If there's a spotlight, you need to check if the spotlight is red. If it is red, then you stop. And you keep on checking whether the spotlight is red or not. And as soon as you see that it's not red, it's going to enter this no part and it's going to keep going. If the spotlight is from the beginning not red, then again it's just going to keep going. The next thing you're checking is if there is enough gas in the car. And if it is true, then you'll keep driving forward. If it's not, then you will find a petrol station and buy gas and then keep driving forward. So this is what a decision tree looks like. Okay, and so decision trees are nothing but a bunch of rules that you will be applying in your on your data in order to be able to classify them properly. Now, decision tree follows something called recursive partitioning. So they are built corresponding to the training data following an approach called recursive partitioning. And what does that do? It splits the data into multiple subsets on the basis of feature values. So on the basis of the different properties of the data set, the decision tree goes on splitting the data into different sets. Okay, so the properties that are similar, they belong to one set or one subset, and it goes on. So even you're creating subsets of subsets as well. And this thing goes on, the splitting process, and it starts from your root node. Okay, and what is the root node? It is nothing but the entire data set. And what happens from the root node, it's going to select the feature which predicts the target class in the strongest way. The decision tree also splits the data set into multiple partitions, with the data in each partition having a distinct value for feature based on which the partitioning has happened. And this is the first set of branches. Likewise, the algorithm is going to continue splitting nodes on the basis of the feature which helps in the best partition. And this is going to continue, splitting is going to continue till a stopping criterion is reached. And what is a stopping criterion? So these are the usual ones. Number one is where you have all or most of the examples at a particular node have the same class, or all the features that you had, that means all the attributes that you had for partitioning, they all have been used. And the third thing is that if your tree has grown to a predefined threshold limit. Okay, so if your tree has reached a limit, a threshold limit, and it's big enough and you don't want your tree to grow beyond that, then also you can stop. Now here is an example of a decision tree. So what you see here are different rows with 5 properties. You have CGPA, communication, aptitude, and programming skill. Okay, now based on these 4 combinations, you have to decide if a person is going to get a job or not. So all different things are given, like CGPA can be high, medium, or low. Communication can be good or bad. Aptitude can be high or low. And programming skill can be good or bad. So with these combinations, what are the chances a person gets a job? And so we are given this data, which would be our training data. Okay, and the test data is where we are going to ask about Chandra, whether Chandra is going to get a job. Given the conditions that Chandra has a high CGPA, her communication is bad, aptitude is high, and programming skills are bad. Okay, so given these things, with these conditions, would Chandra get a job? So there are many ways you can implement a decision trees, but the most prominent ones are this E5.0 or the CART method. CART method is classification and regression tree. You also have the KIDE method, which is the chi-square automatic interaction detector. And finally, you have the ID3 method, which is the iterative dichotomizer 3. These are some of the algorithms that allow you to implement the decision tree. Okay, the biggest challenge is to find out which feature to split upon, okay, which feature to pick so that you can split. And the main driver for identifying that feature is that the data should be split in such a way that the partitions created by the split should contain examples belonging to a single class. And if that happens, then the partitions are considered to be pure. And to measure that purity, we have to calculate entropy. So entropy is a measure of impurity of an attribute or feature adopted by many of the algorithms that we use to implement decision trees like ID3 and C5.0. Now let us say that S is the sample set of training examples, and the entropy measuring the impurity of S can be defined like this. So this formula right here is showing you the entropy. So entropy is minus pi log base 2 of pi. Okay, we'll apply this in practice as well. And here you have a constant right here, up here, you have this constant. So that constant is the number of different classes or labels that you have, that you want to define your tree into. And the P that you have is the proportion of values falling into the ith class label. Okay. The next thing we have to measure is the information gain. So what is that? Information gain for a particular feature A is calculated by the difference in the entropy before a split and entropy after a split. Okay, so entropy before a split, BS, after a split, AS, and it is given like this. So entropy as before split minus entropy after split. Now let's go back to our example of CGPA communication, aptitude and programming skill, determining whether job is offered or not. Okay. Now what we have to do with this kind of an example, first of all, we have our original data set. So what we are going to do first is count how many times yes is coming in a job offered and how many times no. And if you go back and check here, count the number of yeses and number of nos, you will be getting 8 yeses and 10 nos. So that makes a total of 18. And if you calculate the probability, which will be 8 by 18, it will be 0.44, and 10 by 18, which will be 0.56. Okay. And next, we want to calculate the entropy. So to calculate entropy, we have to use the same formula that we saw previously, which is minus pi into log base 2 pi. So if we do 0.44, if we apply this, instead of pi, if we write 0.44, we will be getting 0.52. And instead of pi, if we write 0.56, we will be getting 0.47. And then the total of both is 0.99. And that's your total entropy. This is way before you have made any split. Okay, now we are going to try and split the data. So first we'll try to split on the basis of CGPA. So first of all, how many types of CGPAs do you have? So you have high, you have medium, and you have low. So there are 3 types. So let's first try to split according to high CGPA. We're going to count the number of yeses, which are 4, number of no's, which are 2. Total is 6. And now we will calculate the PI. So PI is, of course, 4 by 6, which is 0.67, 2 by 6, 0.33. Calculate entropy like this. So this is the entropy, and this is the total. And to calculate total entropy, we will be adding these two, right? So total entropy is actually calculated on the basis of the addition of the values that we have, and then find the pi star log pi of that. Okay, so total entropy is calculated here, and we also need to find out the information gain. So how do we know the information gain? You'll notice that we've calculated for high, we have calculated for medium, we have calculated for low. Okay, and everywhere we have different numbers of yeses and nos. So we have here 4, 3, and totally 7. We calculated all these values based on that. Here you have 0 and 5, total 5. Calculated all these values, we got a 0 over here. Okay, and now we need to calculate information gain. So how do we calculate information gain? This is our current entropy. This is our past entropy before doing the split with CGPA. So if you subtract the two, if you subtract from 0.99, you subtract 0.69, you will be getting 0.30, and 0.30 is our information gain, which means if you do this split on the basis of CGPA, then the information that you will gain is 0.3. Okay, the larger this value, the better for you. So in this case, it is only 0.3. Next time we are trying to split using communication, and for that we have just good and bad 2 parameters. So once again, we are doing all the calculations and getting the total entropy, which is 0.63. And if you subtract 0.63 from 0.99, which is our original entropy, you will be getting 0.36. Okay, so this is our current information gain out of communication, which is slightly larger, higher than CGPA. Okay, let's take a look at the next attribute. We have aptitude, which can be high or low, and we are performing the same calculations for these two as well. And here you can see the total entropy is 0.52. Here it is 0.47 information gain, which is much higher than the other 2 attributes that we checked, right? And you also have the programming skill, which can be good or bad. And once again, here total entropy is 0.95. Information gain is only 0.04. So this is of no use for us, but we know that aptitude is having the highest information gain, and that's why aptitude will be the attribute based on which we are going to do the splitting the first time. So this was our original data. This is the data where we are splitting it out. So we have selected aptitude as high and splitted all the data. So this is the data where aptitude is high. Okay, the reason why we have selected aptitude high is because we have these jobs which are so many yeses when the aptitude is high. So we have only kept those rows where the aptitude was high, which is why aptitude column is removed, and we have now 3 of these columns. So we have to keep on splitting. This process of splitting will continue till you have reached one of those stopping conditions we talked about earlier. So we are going to move to the next round this time. Okay, this is level 2. And this time, again, we are going to perform splitting. So this time we have 8 yeses and 3 nos, and this is our total entropy. And we have only 11 rows. Now we are going to try and do the splitting according to CGPA. We got total entropy as 0.33, information gain as 0.52. Okay, because we just subtracted 0.85 minus 0.33. We got this value. Okay, let's try for another one. So we have communication, for which entropy is 0.3 and information gain is 0.55. And if you do the same for programming skill, you will have entropy 0.8 and information gain 0.05. Okay, so if you calculate, if you check the information gain, this one is 0.52, this one's 0.55, so this is the largest one, which means the next feature we will split upon is communication. Okay, so we are going to split upon communication. So let's take attribute equal to high and communication equal to bad, and take out all the remaining rows. You could pick anything here. So we are picking these 2 parameters and taking out the remaining set of rows which are here. And now you're going to start again, try to split. So you will see here now that the entropy is 0.81. Okay, total entropy before you start your splitting is currently 0.81. And previously, your entropy was about 0.85. So we don't want our entropy to go on decreasing, right? We don't want entropy that is less, but we will try out with CGPA and programming skill. So for CGPA, we get an entropy of 0. Information gain, obviously 0.81. This one is 0.5, information gain 0.31. Okay, so the obvious choice is CGPA. Okay, but the information gain is 0.81, and that's the maximum possible gain. After that, we are not able to get anything more than that, right? Because before the split also it was 8.81. So it is obvious that you can apply a split on the basis of CGPA, but you don't have to do anything after that. We will not continue because the information gain attained is maximum. So this is what our diagram looks like. This is where you start. You check if what's with the aptitude. If aptitude is high, you proceed. If it's low, there is no job offered. Check with communication. If it is bad or good, if it is good, then the job is offered. Okay. If it is bad, then you will still check the CGPA and you will check if CGPA is high. Okay. It doesn't matter if communication is bad, but if CGPA is high, job is still offered. And if it is medium or low, then the job is not offered. Okay. This is based on the entropy calculations that we did earlier. So this is our example. You can check the values of the entropies over here. Okay, based on all these entropies, we are trying to split our data. Okay, okay. So this is the final decision tree that we have created, and now we can check if Chandra will get a job or not. Right. So for Chandra, the condition was that CGPA was high, communication was bad, aptitude was high, which means you have to follow this bold line here. So aptitude is high, communication is bad, so keep proceeding on this highlighted line. And programming skills are bad, but that doesn't matter. We haven't included that in the split. So let's check CGPA, which is also high. So which means Chandra will get a job. So let's first take a look at what the algorithm looks like. So initially you have a training data set and a test data set that will be provided. Okay. And what are the steps? For all attributes, you will calculate entropy EI of attribute FI. Okay. And if you check that EI is less than the minimum entropy, then you are going to do this. You will consider E minimum, you will change it to the entropy of your current attribute, and F minimum will be your current feature. And afterwards, you're going to split the data set into subsets using the attribute F min. Okay, so you will draw a decision tree containing the attribute F min and split data into subsets accordingly. And you will keep on repeating it till the full tree is drawn, covering all the attributes of the original table. So we already saw an example in the previous video, so I don't think this is very hard to understand. Now, there can be overfitting in your decision tree, okay, because sometimes the data is overfitted in the sense the training data set is so well organized or so well predicted by your decision tree, but it does not work that effectively when you use a test data set. So to avoid this problem, you would have to do pruning. So what is pruning? It reduces the size of the tree such that the model is more generalized. We don't want your model to stick to the training set. It has to be able to classify the test set properly. And so we can reduce the size of the tree so that it can classify even unknown and unlabeled data in a better way. And there are two ways to prune. One is called pre-pruning. So this is where you stop growing the tree before it reaches perfection. And there's also post-pruning, where you allow the tree to grow entirely, and then you remove some of the branches from it later. Now, what are the advantages of having a decision tree? So it produces very simple, understandable rules, right? And if there are smaller trees, you do not need much mathematical and computational knowledge to understand this type of a model, and it works well with most of the problems. It can handle numerical as well as categorical variables, and it can work well with a small data set as well as a large data set. It also provides you a definite clue of which features are more useful for classification. Okay. What are the disadvantages? So in a decision tree, you often have bias towards features which are having more number of possible values. Okay, so if there are features that have more number of values, then the decision tree gets biased towards those. It can get easily overfitted or underfitted, for which you have to perform pruning. And they are also prone to errors in classification with many classes and relatively small number of training examples. Okay, so if you have problems, classification problems where you have lots of classes, but you have small training examples for each class, your decision tree might have errors. Okay, and it can be computationally expensive to train. So that is another disadvantage. And finally, large trees are complex to understand. A smaller tree is easy to understand, but if it's large, it gets very complex. Where are decision trees used? So they can be applied in a data set in which there is a finite list of attributes. Okay, so you shouldn't have a data set where you have lots of attributes. There should be some finite number of attributes. And each data instance would store a value for that attribute. For example, CGPA high, you should have some values for that. And it can be applied when each attribute has a small number of distinct values. For example, we had CGPA high, medium, and low. But if we had like 10 different CGPAs, this wouldn't be a good choice of model. And it is also should be easier and quicker for the decision tree to make an effective solution if each attribute has less number of values. And so it can be extended to handle real value attributes also, like floating point or temperature. Now, a decision tree can be used even for some instances with missing attributes, okay, or errors. And that is why it is also very effective when you're classifying things which have missing attributes as well as errors. Now we're going to move on to a program for decision trees. So here we have a program for a decision tree right here. Okay, so what you see first of all over here is where we are importing all our libraries. So the first library imported is the pandas library, which we will be using for reading our arrays and reading our CSV files. Next, we have sklearn library. From sklearn, we are importing three things: model selection, because we want to use the train test split module in order to be able to split our data into training and test set randomly. We will also be using accuracy score to calculate from metrics, sklearn.metrics, to calculate the accuracy of our model once it is created. And from the tree module, we will be getting the decision tree classifier to actually implement our decision tree. The first step, as usual, if you have seen other algorithms like KNN and the naive Bayes classifier, you would know this is the first step, which is to read the CSV file, which I've uploaded on GitHub at this link. Once you've read the file, you will first print the first 5 rows. So these are the first 5 rows of your file. And as you can see, this is once again the same kind of data that we have been using for the last 2 algorithms. It's a very simple data that contains 7 attributes, and those 7 attributes give you a value of class, which contains either 1 or 0. So there can be 1 or 0 class. And as you will notice, all the other attributes are actually numerical data. So like we said earlier, decision trees can work well with even numerical data, quantitative variables. It's not just about categorical variables. So this is some numerical data that is being used. And from this, we know that attributes 1 to 7, they are going to be predictors because those are the attributes that will predict the value of class. So we will separate them out. And for that, we will use ilog function of the pandas library. And here you can see we are specifying this range from 0 to 7. And in Python, we know that if you provide 0 to 7, it's going to take 0 to 6. Okay, because the last value is not included. And next we will have the target. So the target will be the class that we want to predict, which is actually named class here. So that will be our last column, which is the 7th column. And that's why we have mentioned the index 7 over here. Now our next step is going to be to split the data. So we are splitting the data into training and test data sets. And for that, we will use the train test split function, which you can see right here, where we will pass the predictors that we created, that we separated out earlier. We will also pass the target that we separated out earlier, okay, and provide the test size. So ideally, you would have a test size of either 0.2 or 0.3. And what that means, if it's 0.3, it means your training data set is 70% and your test is 30%. If it's 0.2, it means your training size is 80% and test size is 30%. And next, you also have the random state. So random state specifies how much quantity or amount of randomness you want to add while creating this training and test data sets. Okay, so we don't just want all first 70 rows to be training and last 30 to be test. We want that to be done randomly. So once it is created, it will return to you these 4 attributes. One is the predictors train attribute and predictors test attribute. It will also split your target column into training and testing, which we will store in these variables. Once that is ready, our next step is to calculate the entropy. We saw how to calculate the entropy earlier, right? In our example where we calculated entropy manually. Here we have a program to do that for us. And in this case, we are using a variable called D-tree entropy to calculate it. And we will we will use the decision tree classifier that we imported earlier. And the criterion here is to calculate entropy and use that to classify the decision tree. The random state mentioned is 100. So once again, we want entropy to be calculated using random rows and columns. So we are mentioning the random state. The maximum depth we want is 3, which means I don't want to go on calculating entropy till all columns are exhausted. I want to calculate till the decision tree depth is 3. So if the decision tree goes beyond the depth of 3, then I want to stop. I don't want to any longer calculate the entropy. And also the minimum sample leaves. So that means the in a tree, the bottommost nodes that you have, those nodes I want minimum 5. So I want a minimum of 5 of those nodes and a maximum depth of 3. When the maximum depth of 3 is achieved, the recursive algorithm or the recursive partitioning will stop. Okay. Once that is done, you will be creating this model where you will try to fit the predictors and target training data onto your decision tree using the entropy calculated, right? So D-tree underscore entropy. And once the model is trained, you will do the predictions using the .predict function and pass the predictors test data, not the other data, right? You just pass the test data and calculate the accuracy score by using target test and prediction. So prediction is something that your decision tree gave you. Target test is the data that we originally had. So it's like we had all these answers to these questions, right? But now we are going to check if the model gave us the correct answers or not. So this is target test. This is prediction that we predicted using the model. And so target test is the actual real values, okay? And we want it normalized out of 1. So we have 0.8437 as our accuracy of the decision tree.